Unit 5, pages 1 through 10, Energy, Work, and Heat. We'll start by looking at two very common types of energy. Kinetic energy, which is energy of motion, and potential energy, which is stored energy, such as in a firecracker, spring, or battery. Kinetic energy is an object in motion and would be described by the equation energy is equal to 1/2 the mass times the velocity squared. The tremendous destructive power in a car accident occurs when the kinetic energy of the moving car is converted into potential energy to bend and break the mechanical component of the car. Note that the kinetic energy depends on the square of the velocity. A car moving at 60 miles per hour, or 26.82 meters per second, has 4 times the kinetic energy of a car moving at 30 miles per hour, or 13.41 meters per second. When the speed of the car increases from 30 to 60, the energy changes by a factor of 4. Potential energy. The stored energy is potential energy. Here are some examples. An apple of mass m sitting at a height h against the force of gravity, g. And so potential energy is calculated with E equals mass times gravity times height for this particular apple. Other examples include a compressed spring. A firecracker releases chemical energy when it explodes. A battery holds stored chemical energy. So, conservation of energy. In chemical and physical processes, energy is neither created nor destroyed. Look at the picture of the pendulum. Here is where we have potential energy, and then as it's falling in motion, it has its kinetic energy. Here's where the kinetic energy is at its maximum, and then when it's at its highest point, that's when the potential energy is at its maximum, where the velocity is equal to 0. At the very bottom of the figure, all of the energy is in the motion of the pendulum. This is the kinetic energy. As the pendulum swings upward, kinetic energy is being converted into potential energy. The speed slows down. The potential energy in the form of the mass of the pendulum being raised against the force of gravity. When the pendulum reaches its maximum height, the direction of velocity reverses. For a split second, the velocity is 0, and therefore the kinetic energy is also 0. At this point, all of the energy is stored as potential energy. A perfect pendulum swings back and forth forever. During the motion, kinetic energy is converted into potential energy on the upswing. On the downswing, potential energy is converted back into kinetic. But energy is never lost, and the motion continues forever, and this is the law of conservation of energy in action. So in this course, the type of energy that we're going to focus on more is going to be heat and work, which is what typically occurs with chemical systems. So thermodynamics does not divide energy into the two forms kinetic and potential. Instead, thermodynamics uses heat and work as the main classification of energy. Work is a force moved through a distance. To identify a process as doing work, something must move, and the movement must be against a force. So here, work is equal to a force times a distance, where you have a force moving an object, and it has to actually move a distance. There are several basic types of work we will deal with in this course. A force that moves an object against a distance, work is equal to force times distance, is expressed here with this equation. An object moved against the force of gravity, for example, could be work equals mass times the gravity times the height, where the object were to fall, and it does work because it does it against the force of gravity. And here are the units associated with that equation. Work is going to be in joules, which is a very important unit to memorize, that work is in a unit of joules. Gravity is 9.8 meters per second squared. Height would be in meters, and mass would be in kilograms. Pressure volume work. Now this is actually something you see the most of in chemical processes. So it's for a constant pressure process, work is equal to the negative pressure times the change in the volume. Notice a change in volume. So that would tend to either be a compression or an expansion. And it's going to be a force that's working against an external force. So work is equal to negative P delta H. Another equation worth noting, that work is going to be in joules, which is going to be equal to atmosphere times liters in this case. And you have your pressure in atmospheres and your change in volume in liters. And then there is electrical work, is another type of work that we find in chemical processes. Heat and temperature. Temperature measures the average kinetic energy content of a sample of particles. So you should relate the word temperature to average kinetic energy. Recall from the theory of gases that the particles are in constant random motion. Each particle has a different energy with a random velocity described by a Boltzmann distribution. We're going to see quite a bit of Boltzmann distributions in this unit and future units. When temperature increases, average energy and average speed of the gas particles also increases. So temperature increase, average speed is going to increase, which is because average energy increases. So it's a direct correlation between the three. A higher temperature indicates the sample has a higher average energy content. So if you were to represent this with, say, arrows, then a short arrow is showing you a lower average energy and a lower speed, whereas you have a long arrow that's going to represent a higher average energy or a higher speed. So this is what you would see if you're looking at a cold low temperature, and this is what it would look like if you were diagramming a hot high temperature. Heat is a transfer of energy through the random motions of molecules. So you should note that heat always moves from hot to cold. And so here we have our hot particles, our cold particles, and they're in direct contact, and notice the energy is moving from the hot to the cold. When you reach a state of equilibrium, they've both reached the same temperature. If we look in the margin to the left, we can see that temperature measures average energy, and this is a Boltzmann distribution. So notice it's this number of molecules versus the velocity, and we have different temperatures. At 300 Kelvin, the lower temperature, the particles are moving at a slower velocity on average. So notice that our peak is at 1,000 meters per second. But once we get a higher temperature, we get a lower curve, and the average energy ends up being a higher velocity for particles at higher temperatures. And that's how you would read this Boltzmann distribution. The average speed increases when temperature increases. The particles in the hot object in the figure have higher average energies compared to the cold object. Energy flows from the hot object to the cold object through collisions between the particles of the two materials. Through collisions, the average energy of the particles in the cold object increases. At the same time, the average energy of the particles in the hot object decreases. This is a transfer of heat. When the energy transfer stops, both objects will be at the same temperature and will have the same average energy content. The average energies of the particles will be the same for both objects when they are at equilibrium. Example 5.1. Discuss how energy changes between different forms when an apple falls from a tree and comes to rest on the ground. So here you have your tree, and there's an apple that's hanging from the tree, and here's our ground. And so right now, as the apple is sitting in the tree, it contains potential energy. And you could represent this with mass times gravity times the height is the amount of potential energy the apple has. When the apple begins the process of falling, then it has kinetic energy, which is going to be equal to 1/2 the mass times the velocity squared. So it has to have velocity in order to be kinetic energy. And then what happens to the energy once the apple hits the ground? Well, the energy has to be conserved, but we don't have potential energy here because it's not at a height, and we no longer have kinetic energy because it's not moving. So what energy do we have? Well, the energy has been transferred into the ground in the form of heat, and that's how the energy was conserved. So when the apple is suspended at a height h above the ground, all of the energy is in the form of potential energy. As the ball drops, the speed accelerates. Potential energy is being converted into kinetic energy, the energy of motion. Just before the ball hits the ground, all of the energy is kinetic. When the ball hits the ground, the energy is converted into the random motions of the molecules in the ground, and this is going to be heat. Example 5.2. Discuss how energy changes between different forms when a car in motion suddenly comes to a stop as it crashes into a solid metal wall. So if you have a car and it's moving, then that is the kinetic energy in the car. And then as the car suddenly comes to a stop because it crashes into a wall, then once it hits the wall, the energy must be transferred as heat into the wall because the car is no longer going to be moving, therefore no longer has kinetic energy, but it also doesn't have potential energy, and so it's being transferred as heat as it impacts the wall. Now, as we look at this diagram, when the car crashes, we also have to note that the car does not stay intact when it hits the wall. So while we have some of the energy transferred into the wall as heat, we also have the car being disfigured or compressed, which means that a force times a distance has occurred with the parts in the car, which means there must be some work being done on the car along with the heat that's being given off in the impact of the crash. Here's your note card for this section. Kinetic energy is equal to 1/2 the mass times the velocity squared, and potential energy is mass times gravity times height, and gravity is 9.8 meters per second squared. This can also be described as work. Work is equal to mass times the gravity times the height as well, and both of these are in units of joules. Work in joules is equal to a force times a distance. We usually are going to be looking at expansion and contraction of gases, and solids and liquids are going to be considered negligible, and that's a very important thing to remember. Work is equal to the negative pressure times the change in volume. We can actually determine the change in volume using the ideal gas law, PV equals nRT. When we rearrange it, we get delta V is equal to the delta N RT over P. Notice that delta N is going to be the change in moles only for gases in the reactions. So the moles of products that are gases minus the moles of the reactants of the gases is going to equal to our delta N. And then R is going to equal not what you would expect, which used to be 0.0821, but because we're dealing with work in joules, we want to use R equal to 8.314 joules per mole Kelvin. Heat moves from hot to cold, and here's our little diagram of conservation of energy, just to kind of remind us to consider that in transformations of energy, it must be conserved.